Testing. 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 All right. We are live. All right, hello and welcome to another Hoopo stream. Today we are going to be doing some paper reading. This is a paper that is currently, I think it's been accepted to iClear 2023. And this kind of follows the theme of the computer vision type stuff that we've been doing this week. Getting into the weeds, this paper is called SparK, which is a ConvNet that's pre-trained with BERT. It should be kind of interesting. The official paper name is here, Designing BERT for Convolutional Networks, Sparse and Hierarchical Masked Modeling. 10 January 2023, so really recent here, and the work comes out of ByteDance, which is the parent company of TikTok, I think, and then Peking University and University of Oxford, so a couple different educational institutions, and then ByteDance being the kind of one who probably paid the bills for the actual training. I have it open here, the PDF in PaperPile, which is a program I use to organize and annotate my PDFs all from the browser. So, get to all right. Abstract. We identify and overcome two key obstacles in extending the success of BERT-style pre-training, or masked image modeling, to ConvNets. Okay, so pre-training is the process of taking a network and training it on a very large corpus of data such that it will have a better starting point for a specific application downstream, right? So it's training that you do before the actual training, pre-training. A very common form of pre-training, especially for something like a ConvNet, is ImageNet, where you pre-train it on the ImageNet classification task. But over the years, that's kind of become less and less popular, and nowadays, the pre-training will tend to use something a little bit more unsupervised, such as masked pre-training, where you basically cut out different parts of the image, and then you try to reproduce those parts of the image. And these unsupervised tasks are more popular for pre-training because they allow you to train on larger data sets that aren't labeled. And those are pretty much the standard, these like large unlabeled noisy data sets. So we're seeing more and more kind of bag of tricks develop as this kind of large pre-training with masked unsupervised learning objectives becomes the de facto standard. So let's see what they do in this paper. So convolution operations cannot handle irregular, randomly masked input images. Okay, and single-scale nature of BERT pre-training is inconsistent with ConvNet's hierarchical structure. Okay, so these are kind of two different issues that you can have when training ConvNets with this type of masked task. So for the first one here, we treat unmasked pixels as sparse voxels of 3D point clouds and use sparse convolution to encode. Okay, this is the first use of sparse convolution for 2D masked modeling. Sparse convolution, there'll probably be a nice picture of it, but it's basically when, here, in this image here, you have a ConvNet, and you can see that in a ConvNet, every pixel and every neighboring pixel get fed into the same kind of kernel that goes and convolves around an image, right? So every single pixel is taken into account. In a sparse convnet, it might be every other pixel, or here they show it with these kind of white empty points. So sparse just means that basically you have a bunch of zeros here. And we'll see what they mean here. Sounds like they're showing you how it affects the data distribution. All right, and then to solve this second pain point here, we develop a hierarchy decoder to reconstruct images from multi-scale encoded feeds. Okay, we develop a hierarchical decoder. Okay, so maybe different levels of decoding to reconstruct images from multi-scale encoded features. Okay, so they might be doing something where they go in at different levels of the convnet, right? Different hierarchies of the convnet, which slowly converts an image into a feature. Our method called sparse mass modeling, or just SparK, is general, and it can be used directly on any convolutional model without backbone modifications. We validate it on a ResNet and a ConvNext. So ResNet is a pretty standard convnet. It's a residual connection network. There's ResNet 50s, ResNet 101, so there's like kind of larger, smaller ResNets. They're not like super popular anymore. I would say vision transformers are much more popular than ResNets. And then ConvNext, this is actually, I think we do have a stream for this paper as well, but it's basically a convnet that people designed after the vision transformers took over, and it has comparable performance. So convnets aren't entirely dead yet, and that's kind of what they mean here by a modern convnet. It surpasses both state-of-the-art contrastive learning and transformer-based mass modeling by similarly large margins, around 1%. The improvements on object detection and instance segmentation are more significant, validating the strong transferability of features learned. Okay? And yeah, this is the whole point of doing pre-training, is you want to be able to fine-tune it to some specific task, and you want the features that are learned by the convnet in the pre-training to be useful when learning this new task, right? The transferability of those features. We also find its favorable scaling position by observing more gains on larger networks. All this evidence reveals a promising future of generative pre-training on convnets. Okay. Onto the introduction here. They have very long style citations here. Like, these are kind of annoying. It would have been nicer just to do the little number styles, but maybe they wanted to fill paper. The pre-trained fine-tuned paradigm in natural language processing, popularized by BERT and GPT, is remarkably effective and thus long envied by our vision community. I would say that it also exists in the vision community as well. Pre-training and then fine-tuning is pretty standard in computer vision as well. It is the emerging masked image modeling that initially extends the success of BERT from language transformers to vision transformers. Yeah. I would say these masked tasks are... I've seen it way more for vision transformers. I really haven't seen it for convnets, so this is why we're reading this paper. Bold move that increases the mask ratio to a staggering 60 to 75% and is largely credited with this success. Yeah. Mask ratio of 60 to 70%, which means 60 to 70% of the image is actually empty and you're reconstructing 60 to 70%. And the field of visual self-supervised learning on VITs has now shifted from contrastive learning. So this is actually the papers that we were reading earlier this week. Locked image tuning, this is a form of contrastive learning, to BERT-style masked modeling, or a fusion of them. Extending the success of BERT pre-training from transformers to convolutional networks is a wonderful but unrealized vision. The pioneering work preceded BERT but performed much worse than supervised pre-training. There have been efforts over the past year trying to port BERT to convnets, yet eventually compromise on proposing non-convolutional models or non-masked modeling. One may therefore ask what exactly is preventing the application of BERT to convnets. Okay, so basically people have tried to do this kind of stuff before, but something happened, and I bet you they're going to present what they did to fix it. We try to conclude that, in essence, the difficulty is rooted in the gap between language and vision in terms of data processing. Typically, NLP models like recurrent networks or transformers process text as a variable length sequence of words, while convnets have to recognize objects of different sizes from raw pixels. This huge disparity raises two challenges. Removing the information of masked words is difficult for convnets. For VITs, an input image is divided into several non-overlapping patches. Yeah, this is important, right? VITs, which is a vision transformer, basically it turns an image into words, right? And the way that it turns an image into words is, or not actually, but kind of the equivalent of words, right? Because transformers are about sequences. So how do you turn a 2D image into a one-dimensional sequence? And the way that you do it is you basically cut up the image into these little patches. For example, VIT16 would cut it into 16 of these patches. And then that actually makes it very easy to do these kind of masking tasks, because you could just simply remove a bunch of those patches. Simply dropping masked patches or replacing them with masked tokens can remove the information. This ease relies on transformer being able to handle irregular variable length and non-overlapping patches. Cannot be achieved on convnets, as they do not only operate on regular grids but also perform sliding window with overlapping. Yeah, so that's an interesting thing to think about, is that because in a convnet you're kind of convolving this kernel through your whole image, if there's parts of your image that are zeroed out, any kind of convolution that even barely touches that is going to be messed up, right? One may zero out all masked pixels and feed this mosaic into a convnet. This, however, leads to a severe data distribution shift and other issues, and thus cannot be an ideal solution. Okay, so this is actually what they're talking about here. Is that, let's zoom in a little bit so you can. But if you notice here in a transformer, right, they have this picture of a cheetah, right? And here you have a data distribution. So this is just kind of showing you the different values of pixel intensity over this whole image of a cheetah, right? So there's a lot of pixels that have, I don't know what this is. This is a value of 0. This is negative 0.1. This is 0.1, right? This has been normalized to negative 1 to 1. And you can see here with the transformer, first thing you do, you turn it into patches. So this is a VIT16, right? 4x4, 16 different patches. And you can very easily just zero out some of those patches, and then the way that those feed through the transformer architecture, because the transformer is just doing kind of attention, it doesn't matter, right? The 0 multiplies with the 0 and becomes 0. The 0 multiplies with something and just stays 0. So it's like the parts that are zeroed out kind of stay roughly the same. So you're not really impacting this distribution of the data here. So I think they're showing gray is the before and then blue is the after. But if you were to do something with a convnet, right, similar, so here the cheetah, it's not cut into this grid, but basically they're convolving it. So they zeroed out the pixels, the same pixels that would be zeroed out in the kind of patch-based masking here. But when you do that, each subsequent feature map, as you go higher and higher in this hierarchy of convnets, is going to have a bunch of zeros in it, right? And you're kind of going to fundamentally change the distribution of data that's being fed through each subsequent layer of this convnet. And that's kind of what they're showing you here, is that you're going to have a huge amount of weights and numbers in your convnet that are basically very, very close to 0, because you're here, right? This point here on this layer of the convnet is basically the convolved part of this kind of 9x9 grid here, right? So there's 2 zeros in that. This is going to become very small. So you kind of have this problem where the zeros kind of propagate and kind of start mucking about in your convnet. So that's the whole point that they're trying to say here, is that kind of this masking task, kind of just the way that convnets work, the way that convolutions work, they kind of have this data distribution problem if you do a masked learning task. Single-scale algorithm cannot learn multi-scale features. Multi-scale structure has long been a gold standard, which allows visual processing systems like SIFT, which is a scale invariant feature transform. This is a very old school. And pyramid networks, which is kind of a similar idea where you're basically, not similar idea to SIFT, but similar idea to multi-scale hierarchical stuff, where you basically have different resolutions of the image, and some of your features are being generated from like a very small kind of little tiny thumbnail of your image, and then some features are getting generated from the larger image, and that leads to features that can pay attention to kind of different scales within the object. Yeah, so these are usually done to cope with changes in object scale. In contrast, mass modeling from NLP originally works in a single scale manner. In this work, we clear the hurdles above and make BERT suitable for ConvNet by proposing sparse masked modeling with hierarchy. Why is this all red? It first randomly masks images in a patchwise manner. Observing the sparse nature of point clouds coincides with these unmasked patches. We treat them as a flattened 3D point cloud and use sparse convolution for encoding. Okay. I don't exactly know what they mean here by this, but this strategy accurately eliminates the information of masked parts while allowing convnets to easily handle irregularly masked images. We fill in all empty positions on the multi-scale features with mask embeddings, then feed them into a multi-scale decoder. Okay, I think this might actually be the key sentence here, is where rather than kind of just feeding in a 0 into the parts of the feature map here that have contact with the 0 patches, right, these masked patches, what they're going to do is they're going to fill those empty positions with features, non-zero features of the previous layer. So it's like they're basically masking at every hierarchy level. That's kind of what it seems like they're suggesting here, but we're going to have to keep going to figure out what the actual thing they're doing is. SparK is a general method that does not limit the specific encoder to be pre-trained. We tested with 2 representative convnets, so your kind of standard resnets and then your convnexts, which is kind of a more modern version of the convnet. More gains on larger models. Standard development tasks, so they tested on some kind of generic things here: classification, object detection, and instance segmentation. SparK outperforms state-of-the-art contrastive learning and transformer-based masked modeling by similarly large margins. This is kind of an interesting claim. Like, if this is true, that would be pretty intense, but they're probably cherry-picking, and they probably just picked kind of a weird niche kind of benchmark that other people haven't tested on, because benchmarks to me are all about the data set, right? Getting state-of-the-art on these type of classification object detection benchmarks, like the way you do that is you work at a big company and you have huge proprietary data sets that you can train on for a huge amount of time. I don't think like a small academic institution can get state-of-the-art tasks. So like, I'm kind of dubious of this claim, but we'll see exactly the details of it. The improvements over Cocoa baselines are more significant than those on ImageNet, indicating the representations are highly transferable. First, BERT-style pre-training method that can be used directly on any convnet without backbone modifications. Okay. The insights into designing generative pre-training for convnets. i.e. the first use of sparse convolution for masked image modeling. And then a leap in ConvNet's performance across downstream tasks, showing promise of extending success. Okay. So these are kind of their 3 contributions of this paper. Is we did a new thing, bunch of questions about doing this new thing were answered, and then this new thing seems to perform well. The computer vision community has recently paid more attention to vision transformers. A little pun right there. While ConvNets no longer appear in the spotlights. So it's a little bit more than just performance, right? I think part of the reason that vision transformers have kind of beat out ConvNet is not just a performance argument, but it's also an argument from kind of simplification. I think that people don't want to have like these machine learning frameworks with a million different operations. They'd rather have machine learning frameworks where there's a very small and much more limited scope to these operations, right? And if you can do natural language and vision and speech and text and all of those things with a transformer, that makes it easier to design hardware for machine learning looking into the future, right? Because you don't need to be designing hardware that's going to work well with a ConvNet and that's going to work well with a transformer, because those are kind of different types of operations that you're doing there. So I think that it's not just about transformers having better performance. It's about people seizing the opportunity to consolidate the neural architecture space into a much more kind of narrow scope, so that everyone who kind of designs either hardware or designs things such as CUDA, right? It makes it easier for them because they don't need to be supporting all these different types of neural network architectures. They just need to worry about having a very efficient implementation of a transformer. Okay. So nonetheless, these neural networks that condense the essence, scale, and translation equivariant, locality, weight sharing, blah, 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 of many classical vision processing systems play an irreplaceable role in tackling a wide range of real-world tasks that are more challenging than or structural than classification. Okay, so they're kind of like trying to use some kind of emotional argument for ConvNets shouldn't be dying. I don't know, I feel you could say all of that about transformers too. We hope SparK's and spine performance will prompt us to revisit ConvNets as generic backbones. These guys are good writers. Like, this is very interesting. Like, they're writing this as if they're like, it's like a political speech. For our community and inspire future arts and exploring the potential via generative Okay. So now we're in this related work section here. Hierarchical visual processing systems. So hierarchical is acknowledged as a gold standard for visual representation systems. What they mean by this, like, I think a lot of classic computer vision algorithms did these kind of hierarchy systems because they were honestly pretty bad, so they had to kind of figure out a bunch of bag of tricks to make them work better, and kind of having these hierarchical structures made it work better. But like, I don't know, maybe all deep learning is hierarchical because you basically have layers of these, each neural nets have like layers and layers of repeated things, so kind of a hierarchy by default. Many fundamental handcrafted feature descriptors extract multi-scale visual representations via scale space extremum on a feature pyramid. Proxies to extract scale invariant features, thus allowing the system to cope with varying object sizes. Yeah. This is kind of the big problem, is that the way that you design your ConvNet, it's going to be kind of inherently better or worse at detecting either very big objects in your thing or detecting very small objects. These descriptors also motivate the design principles of convolutional networks. Some recent arts also elaborately design hierarchical modules that allow the information aggregation at different granularities to better tackle detection and segmentation tasks. So this is what I'm saying, but in a better, more poetic way. Okay, recent progress on visual self-supervised learning. Yeah, so to me, the state of the art for these are clip and these kind of like contrastive language image tasks. The lit, the one we saw earlier this week, is also this kind of stuff where we're moving away from supervised learning as kind of the standard paradigm, and now for the past, I would say, 4 years, it's all been about kind of training on the largest possible data set, and these huge noisy data sets, the only way you can really train on them is with these unsupervised or self-supervised tasks. So that's kind of where the whole industry's going. It's like move or figure out the biggest data set you can find, and don't worry that it's not labeled data, just formulate some kind of unsupervised task so that you can train on this huge data set. More advanced methods are developed, and this line of work has dominated the area of visual unsupervised learning until masked generative pre-training along with vision transformers came. Inspired by the recent success of masked language modeling in NLP, masked image modeling has attracted growing interest. So we have pre-trained transformers by learning to predict tokens. This might actually be the deter or clip. Geniusly take advantage of transformers' ability to handle variable length inputs and implement an efficient and scalable method. Okay, regress raw RGBs to simplify the training while way selects hog, histogram of gradients is what this means, as targets due to their rich semantics. Designs a transformer with a heavier patchifier to perform mass modeling. Enormous studies have successfully verified the efficacy of these algorithms on vision transformers. Yeah, so they're kind of referencing that the type of people that are doing this self-supervised learning on these huge data sets is the big companies, right? Realistically, nobody other than Meta and Google and like these big companies are going to be able to do like self-supervised pre-trainings. Not only because they are the only ones who are willing to drop a couple $100,000 on the training, but they're also the only ones that have these large proprietary data sets. Therefore difficult to be used. Convolution is widely used in 2D computer vision, which typically performs sliding window on regular grids. Yeah, so this is really what a ConvNet is doing, and I love to show this image. ConvNet going on somehow. So this is what a ConvNet is doing, right? It's really just sliding this little window across the image, and it's taking the information in these 6 pixels or in these 9 pixels and turning it into one number here. Map. And if you do that enough times, eventually you kind of reduce the dimensionality of your. When faced with 3D point clouds, this operator quickly becomes unaffordable due to the cubic increasing number of grids. Voxels are basically you could think of it as a small little. A picture's worth 1,000 words. Yeah. So in a 3D space, you have you can basically define a grid for each of the kind of 2D planes, and then one individual little cube is called a voxel. Perfect. Pixel, and then voxel. Analogous 3D. Considering point clouds are highly sparse and irregular, one can skip all empty voxels for speed. Motivates the sparse convolution. Just heavily used in modern 3D ConvNets tasks. Minkowski engine is one of the most common sparse conv frameworks. Some prior arts also introduced sparse conv for faster 2D visual understanding. And in this work, we have observed the similarity between 3D point clouds and 2D masked images BERT-style pre-training. Okay, so basically, they still haven't really explained what this sparse conv is, but it's basically a special type of convolution that seems to have been designed for 3D ConvNets, right? ConvNets that work in 3D space, and usually those are dealing with point clouds. But even in 3D, I would say that convnets in 3D are kind of like a very niche thing, because realistically nowadays people use NeRFs and other kind of neural rendering methods. So like convnets in 3D were kind of like a weird branch of the computer vision research progress that to me kind of died out. So it's interesting that they found this kind of specific type of sparse convolution from a dead branch of computer vision research and are kind of reviving it here in this paper. Illustrated in Figure 2, our SparK framework aims to pre-train a convolutional network encoder via hierarchical masked image modeling, masking a portion of image and learning to recover it. Yeah, so this is largely what all your favorite giant AIs are doing, is, or trained on, is basically, for example, GPT, what it's basically trained to do is give a sentence and then what's the next token, or here's a sentence, we're going to remove 4 words, and then can you read what are the 4 words that we removed, right? So this kind of idea of masking, right? Zeroing out part of the input data, and then the task of the model is just to recover the data that was removed. So this is, you can basically automatically generate the label, right? You don't need to have someone tell you what the answer to this particular input is. So that's the whole point of these masking tasks, is that they're unsupervised. Although some people call this self-supervised. There's the word unsupervised versus self-supervised. There isn't like a clear distinction there. Like some people will say unsupervised to refer to masking tasks. Other people will say self-supervised to refer to masking tasks. But the important thing is that unsupervised and self-supervised are very, very different from supervised. That's kind of the key distinction here. And this is very much a unsupervised or self-supervised task. We're going to detail SparK by introducing a sparse masking strategy, a hierarchical encoder-decoder architecture, and the optimization target of SparK pre-training. All right, here we go. You know, part of the reason I picked this paper is because these are very nice figures. Whoever did these, like these little like 3D like images, the kind of, this is a very well done figure. Okay, so now we're finally kind of understanding what they mean by hierarchical here. So as you can see here, you have the image, which is still this picture of the cheetah. It's getting broken down into these patches. And then they're masking out some of the patches, right? They're zeroing out some of the patches. And because it's a convnet, right, the feature encoder at the bottom of the hierarchy, or the feature map at the bottom of the hierarchy, is going to be bigger than the feature map at the top of the hierarchy, right? At the top of the hierarchy, this is going to be, here they have 4x4, then, or 2x2, then 4x4, and then 8x8. So hierarchical, what they're referring to here is that they're going to basically push gradients and kind of have a loss function at each separate hierarchy. So they're going to be comparing this 4x4 to this 4x4, this 2x2 to this 2x2, and this 8x8 to this 8x8. So if they didn't do that, and all they did was just compare the final 2x2 with the final 2x2, then they wouldn't be using the word hierarchical. So the word hierarchical here is basically telling you that they're doing this loss function, and they're comparing the kind of feature maps at different levels of the hierarchy of this convnet. To adapt convolution to irregular masked input, visible patches are gathered into a sparse image and encoded by sparse convolution. To pre-train a hierarchical encoder, we employ a UNet-style architecture. So UNet is, right, if you think of the letter U, it has, it starts high, and then it goes low, and then it goes back high. So that's what this architecture is doing here, right? It starts with a big, and it gets smaller and smaller and smaller. Then it's like the middle part of the U, which is low and small, then it gets big again. So this is kind of what the UNet architecture means. Decode multi-scale sparse feature maps, right? Multi-scale, have different scales here, and the purple stuff here, and then the blue stuff here, this is the feature maps, where all empty positions are filled with mask embeddings. This densifying is necessary to reconstruct a dense image. Only the regression loss on masked patches will optimize. After pre-training, only the decoder is used for downstream tasks. Yeah, so if you look at this image right here on the blue side, there's the little squares that they mask out are empty, right? And then here, if you look on the purple side, the little squares that they masked out are have this like kind of crosshatch pattern. So that's kind of what they mean by empty positions are filled with a mask embedding. Is basically they're filling it here, and they're filling it with, I guess, kind of the average of what you would have if you fed the full image through. And they call this densifying, right? That's not really like a technical definition. It's kind of playing off what's called sparsity, which is where you kind of zero out a bunch of things. So densifying is like you're, I guess, taking these zeros and then actually giving them a real value, which is what crosshatch. We start by the patchwise masking strategy, which is widely used in masked image modeling. An image is divided into several non-overlapping square patches. Each will then be masked independently with a given probability, called a mask ratio. Randomly choose some things to mask. Previous transformer-based mask modeling can easily eliminate the information by directly removing masked patches or replacing them with a masked token. I think this. Or no. Mask token is a 0. Sorry, never mind. So in a transformer, right, you're taking a sentence and you're turning it into little vectors, and those vectors are called tokens. And those tokens represent different words or usually little phonemes and little like parts of words and things like that. And when they when they mask out sentences for these kind of masked tasks or masked objectives, they're not taking those, they're not zeroing out. They're not giving a token that's basically a bunch of zeros. It's like it's going to be some specific agreed upon mask token that they use. This ease relies on the fact that vision transformers are born to handle irregular input and operate on non-overlapping image patches. Yeah, this is the key thing here, is that in transformers, you don't have any overlap, right? This, however, has 3 evident shortcomings. The computation of masked regions is redundant. It would disrupt the data distribution of pixel values, and the pattern on mask maps will vanish after applying several convolutions to this zero-out masked image. We examine problem 3 in figure 3, where we also give our solution. This is figure 2, and then this is figure 3. Let's finish this paragraph, then we get there. Note that this problem is particularly acute when using modern deep convnets due to the large number of successive convolutional blocks. Okay, so let's see what they're talking about here. Using sparse convolution to address mask pattern vanishing issue. 3 mask examples are shown. Okay, so here's different masks. So this isn't the image. This is basically the mask that you would apply to the image. When computing ordinary dense convolutions centered at the 0 mask position, the result would be non-zero if the filter covers any non-zero points. Okay, so think this again, right? So this is what you should have in your head right now. Right, we're going to be moving across this image. So when you have this mask and you move this little filter across this image, you're going to be running, there's parts where you're going to have a bunch of actual data, and then you're going to have a bunch of zeros. So you're constantly like, there's going to be parts of that image when you scrape across them, a bunch of zeros, and those zeros are going to start messing with areas around that, right? So patterns shrink and vanishes due to the erosion effect of ordinary convs. What they're showing. Every time you like convolve around, the kind of like zeros mess with it. Or I guess here they're talking about that with sparse convolution, however, that does not happen. The pattern remains. It skips Okay, I see what's going on. Okay, so think about our little GIF, right? And here, this is the stuff here is showing padding. So usually when you have convolution or padding the but don't worry about that. But basically what they're saying is that if the little kernel, right, this little gray window that's sliding across, it's called a kernel often. If that little kernel happens to have some masked tokens in it, then just zero it out, right? Don't calculate for that. That's kind of sparsify, right? Like basically zero that out. So that's what they're doing here, right? They're saying that this little dotted square here, when the convnet goes over this, because there's a bunch of mask tokens here, we're going to just say the resulting value for that is mask, right? But if there's a bunch of ones, then skip those m's, right? Where m is the mask and then 1 just represents data. So they're calling this the vanishing problem. So largely what they're doing is they're skipping all masked positions and keeping the mask pattern. And this allows the mask to kind of exist at higher and higher levels of hierarchy within the convnet, versus if you didn't do this at the higher levels of the convnet, you would have a dense signal. To overcome these problems, we propose to sparsely gather all unmasked patches into a sparse image and then use sparse convolutions to code it. This strategy ensures no information is leaked, can be applied directly to any convnet without backbone modifications. It's efficient as sparse convolution computes only at visible places. 3 solves the aforementioned issues of pixel distribution shift and mask pattern vanishing. Sparse convolution will skip all masked positions on sparse feature maps and only computes at unmasked points. This helps to prevent the shape of the mask pattern from changing with convolution, thus ensures a consistent masking effect and ratio throughout all convolutional layers. Another fact is that when fine-tuning, all sparse convolutional layers can be naturally reduced to ordinary dense ones. This is true because dense images are actually the special case of sparse images that have no. Okay. By hierarchical encoding, we mean that encoder will generate a set of feature maps with different resolutions, namely scales, right? Taking a ResNet model, it'll typically contain 4 stages, right? 4 layers in this ResNet, each with a series of convolutional blocks and a downsampling module. The feature resolution is downsampled by a factor of 2 after every stage. So if you start with an image of height and width, a ResNet 50, which is actually one of the smaller ResNets, each successive patch or each successive level of this ResNet will have less and less features, right? So that's kind of basically what you see here, is that at the lowest layer, right, the lowest layer in the hierarchy, the lowest layer in your ResNet, your feature map is pretty big. It's probably basically the size of the image, but then as you go higher and higher, it becomes smaller and smaller. Overall, the decoder follows the design of UNet. We use relatively light decoder that contains 3 successive blocks with upsampling layers. Before reconstructing a dense image, it is necessary to fill in all the empty positions on sparse feature maps. This is called densifying. Yeah. Taking the smallest sparse feature as an example, all empty positions, or what they're calling inactive sites, are filled with a mask embedding. Okay, so taking out the green, which is our technical terms here. And then these are the successive blocks. And then you have the sparse feature and then a dense feature. A projection layer is applied then in case encoder and decoder have different network widths. D4 is the input of decoder's first block. It has the same resolution as S4. Similarly, we can get the different inputs for the decoder blocks here. Yeah, so This is basically just a linear projection layer or linear projection operation. So it turns SI such that it has the same dimensionality as D. You can add them. 4 different mask embeddings and projection layers are required. They belong to different scales and may have different network widths. The final output of the decoder is D1. Okay, so here you go. This is D1, D2, 4, S1, S2, S4, and you're using S1 here to densify D1, S2 to densify D2, S4 to densify D4. Kind of what this means here. The arrow that turns from purple or blue to purple. To reconstruct an image from D1, a head module H is needed. So, okay, you have a head on top of your little ResNet here, which should include 2 more upsampling layers to reach the original resolution of input H times W. Or maybe this is not a head for the ResNet. I think this is a head for the decoder. As for the reconstruction target, we choose per patch normalized pixels as targets. Okay, so this is the actual reconstruction loss here. So this is the actual loss that they're using to push the gradients into their network, and it's basically an L2 loss, which is basically here's what the pixel was, or here's what the value of this normalized pixel was, and then here's what the network predicted, and then you do an L2 difference between those and push the gradients back. So pretty standard kind of loss there. After pre-training, we discard the decoder and only use the encoder for downstream tasks. Yeah, so the decoder is just there to perform this pre-training task. But then once you're actually done with the pre-training and you want to use this model to do something like classification or object detection, you're going to be using just this blue part here, right? You're going to feed your actual images and you're going to get a little feature map, and then you're going to use that feature map to do image classification or object detection or whatever you want, right? And really this whole encoder decoder system was really only created so that you could do this unsupervised masked learning. But you never really actually need this decoder anymore once you're done pre-training. Due to the fact that dense input is a special case of the sparse where every position is active. Okay, empirical results. SparK can use any convolutional network as the encoder without any special design of the backbone architecture. We implement SparK with the ResNet and the Conv next. For the masked embeddings, we implement them as random initialized learnable feature vectors. Okay. For decoding, we use a lightweight UNet decoder. Positional embeddings are not used since ConvNets already encode spatial information. Yeah, so in a vision transformer, because you're kind of flattening the image and you're feeding it in patch by patch as if it was a sentence, usually people will also feed in kind of a positional embedding. So in a ConvNet, you don't need to do that. Simple implementation of pre-training. For simplicity, the same hyperparameters are used for all architectures and model sizes. Even though tuning each may improve our fine-tuning performance value. All models are pre-trained with 1.28 million unlabeled images. Big data set here. From ImageNet 1K. And it's training for 1600 POCs. Only the minimal augmentation is required. Okay, not doing augmentation. Cropping and flipping. We use the same mask patch size and ratio as an SIM-MIM. Trained with a LAM optimizer. Batch size. This is a big batch size. They're probably training this on a big GPU cluster if they can get that kind of batch size. And a cosine annealing rate with a peak value of 0.002 times the batch size. use the official implementations of ResNet, Conv next. Performance comparison with self-supervised transformers. Okay, so they're also comparing to these here. So this is a vision transformer. Swin is also a transformer. So they're comparing it to different types of transformers here. Okay, here you go. ConvNets have much more potential than expected, and their capability in visual representation may not be inferior to that of the transformers. Yeah. So in the actual human eye, and pretty much any eye, I think, ConvNets is kind of the way that there is kind of like a ConvNet-like system happening in eyes, right? The way that animals and humans process visual information is more similar to a ConvNet than it is to a transformer. So maybe ConvNets don't die. SparK has the advantage of encoding efficiency, especially compared to contrastive learning that encodes 2 or more images in a forward pass. So in contrastive learning, you're encoding an image and you're also encoding the text, and then you're basically moving those embeddings either closer or further away. For instance, Dino and iBot use multi-crop with 2 global crops of 224 by 224 and 10 locals of 96 by 96. SparK requires only 40% of the theoretical overhead thanks to the sparsity of masked input. 60% of patches are masked, and sparse convolution only processes the rest. We found a sparse ResNet 50 can save 23% memory footprint. Okay, so actually this is why. That's interesting. So when I saw this batch size up here, batch size of 4096, I was like, this is absolutely massive. They got to be training on like a huge GPU or a kind of some kind of distributed parallel setup. But here they're actually telling you that because of this sparsity, the actual memory footprint of the batch is smaller. So that might be why they're able to use have such a large batch size. Although this is still a pretty monster GPU, like a 32 gigabyte Tesla V100. Like that's not a consumer GPU. That's something that you would have in a data center. Something like ByteDance would easily have this kind of hardware. Comparing SparK and self-supervised transformers. All methods pre-trained on ImageNet 1K and fine-tuned resolution. I'm going to very quickly film that. Horribly watch. That was too cute. I have like a test stream on the side so I can make sure that the audio doesn't drop out and that it all looks good. But Boo decided to watch it. Comparing SparK and self-supervised transformers. All methods pre-trained on ImageNet 1K and fine-tuned with a resolution of 4. Top 1, accuracy is recorded and the best results are in bold. Extra model indicates whether Dolly's DVAE, trained on 250 extra data, is used. Okay, so vision transformer backbone, you have all these different works here. pre-training task, you have contrastive learning, you have masked image modeling, contrastive learning and masked image modeling. You have here different backbones. And then you have the accuracy. So they're basically doing this large masked image modeling, and then, or this large pre-training task, and then they're basically trying to see how well it works in just an ImageNet classification task, right? ImageNet 1K. So you can see here that these transformers, right, trained with contrastive learning, are getting around 80% accuracy. And then here they're very proudly showing you that their ConvNet, right, ConvNext, trained with the masked image modeling task that, or masked image modeling pre-training that they talk about in this paper, effectively end up around the same place, kind of around 84. That's kind of cool. Pairing ConvNet-based SparK with transformer-based self-supervised learning on downstream tasks. On ImageNet, the same fine-tuning resolution is 224. Mask RCNM with FPN is equally applied. All methods follow a 3x COCO schedule. So each successive epoch in this learning rate schedule will like slow or make the learning rate smaller and smaller. You see very commonly in deep learning where the learning rate is initially much higher and then it kind of becomes smaller over time. Average precisions of a detection box and segmentation mask. So there's two different tasks here. There's bounding box detection and then there's segmentation mask. Okay, and you have again here VITB. This is a big vision transformer. SwinB, another big vision transformer. Effective epochs, I guess, is just a proxy for how long this was trained. And you have here classification, you have detection, and you have segmentation. So 3 different downstream tasks. You're pre-training, and then you're kind of evaluating on these downstream tasks. And you can see here these vision transformers are kind of roughly around 80% here, which is roughly where this one is. Detection, segmentation. These numbers are all very close, though. You know, it's not like 50 versus 51, 44 versus 45. Like, you know, I wouldn't call this like state of the art necessarily, especially because it sounds like they trained this themselves. So generally when people train, if you're doing a baseline and you're saying, okay, well, I'm going to compare this to MoCov 3. So I'm going to go to the MoCov 3 GitHub and I'm going to use their model implementation, but then train it on my GPUs with my thing and get the final class accuracy. Like, you're not going to get as high of a score as the person who originally wrote the MoCov 3. So I think sometimes these kind of like benchmarks are like a little bit dishonest in that case, where it's like my implementation of my own thing outperforms my implementation of other people's things, right? But you're not really allowed, like if it was your implementation of your thing versus their implementation of their thing, I think the scores might be different. So something to kind of think about here. But largely what I'm seeing when I look at this table is that this SparK method that they're talking about is comparable to basically training a big transformer with a contrastive learning task or a masked modeling task. So it's roughly about the same. They figured out how to do masked image modeling for ConvNets, which is what this paper is about. Previous results have exposed the potential of SparK pre-training. We evaluate the representation quality on fundamental downstream tasks. These tasks are challenging, serving as professional feature evaluators because they place higher demands than classification. Here we consider 2 different settings: comparison with self-supervised vision transformers and then with convolutional networks. Table 2 compares the fine-tuning on 3 downstream tasks: classification, object detection, segmentation. Yeah. ConvNext and SwinB perform similarly. validate that BERT-style pre-training on convolutional networks is promising. Okay, here they're pre-training task, contrastive versus generative. Again, these numbers are basically the same. 7, 8. 79. 6. Like, what this is telling me is that it's just the same thing, right? It's the architecture doesn't matter. The pre-training task doesn't matter. The number of epochs doesn't matter. The only thing all of these are basically being limited by is the data set. When we compare SparK to state-of-the-art convolution, all contrastive methods are basically on par with pre-training. I don't know about perform significantly better. We're talking like 0.05%. To me, that's like kind of on par. SparK does not rely on sophisticated augmentations. I mean, something tells me that they probably did try that. They probably did try to do sophisticated augmentations, found that it didn't actually do that much better, and then they were like, hey, we don't actually need them. It optimizes a reconstruction loss, a form of a regression loss, which is considered to be more dense than contrastive learning instance classification. Most stages are object-centric, while Coco contain multiple disorganized objects. This domain gap poses a challenge to transfer learning, and SparK is demonstrated to fix it. As shown in the last column, one can observe that with our SparK pre-training, all models except ResNet 50 achieve performance on par with their non-pre-trained versions of sizes. Such a qualitative leap indicates SparK can push a ConvNet to the next level in terms of representation capability. All right, so here they're doing it on different sizes of ResNet. So here you have a ResNet 50, which is kind of the smallest ResNet that people use, and then a ResNet 200, which is kind of the largest ResNets that people use, and different sizes of the Conv next as well. So SparK accuracy here. I guess that it's better. Yes, I don't know. Big models are good, small models are bad. You gradually ablate the components and check the corresponding performance. Okay, so what are they going to remove? So ablation studies are great. This is where researchers will remove certain parts of their pipeline and see how different parts affect, or how much impact individual parts of the pipeline have to the final results. So in a sense, it's doing masked modeling for the experiment itself. Okay, so they first removed the sparse masking and the hierarchical strategy architecture. The issue raised by zero outing and mask pattern vanish can lead to ineffective. Okay, so here's the ablation study. So they remove the zero outing without the hierarchical aspect to it, without ape, absolute positional embeddings, and then without with more loss. What are they? Observe calculating loss values on only masked patches. Okay. This is whether or not the loss also includes the non-masked patches. And then pre-train less. Longer pre-training versus... Okay, so basically how long do you train it? So here the ablation study is training for 1600 epochs versus 800. And I don't know, kind of interestingly, it doesn't really seem to fucking matter. Like, these numbers are all the same, so what exactly is going on, right? Not pre-trained. What? I don't understand what's going on here. Like, these guys are making kind of mountains out of molehills, dude. Like, if you're already getting 83% accuracy without any pre-training and you throw the kitchen sink at it and you get 1%, like, what are you actually doing? Barely getting anything out of here. But this is a nice little table, you know? I like this table. All right, finally, visualization. We're almost at the end here. We visualized some reconstruction results to check how the model performs in pre-training. We can see that the model is able to make different but plausible predictions on masked regions. Okay, so this actually shows you what the masking actually looks like. So this is the actual input here, this row, this raw input, and you can see this dog. And then the masked input, so this is where they're going to mask, so you can actually see how the masking looks. It's just kind of like they're randomly zeroing out parts of the image. Prediction plus input, unmasked patches copied from raw input. Okay, so then they're showing you this is what the encoder is learning, right? The decoder, right? So the UNet encoder decoder, it basically, you give it this raw input, you give it the masked input, and it'll give you this prediction plus input, right? It'll give you it'll reconstruct the parts that are missing. So this kind of gives you a rough idea of like kind of how good it is, right? And you can actually see it's kind of good. Like, I'm looking here at these socks and like the continuation of these lines, right? That's quite good. Here, an interesting thing is that in the input, the orange has like a smiley face and an unhappy smiley face, and then when you mask out the unhappy smiley face, the reconstruction doesn't have that smiley face anymore, which makes sense. Here, for example, this bird has like a little yellow or a little white chin and then like this little crest, and when you reconstruct it, it kind of loses that. So yeah, I mean, this seems kind of reasonable. It's not absolutely crazy, but about what you can expect with masked fiction. All right. Now let's get to conclusion. The NLP community has witnessed the rise and proliferation of masked modeling and transformers, followed by the recent efforts to validate this paradigm on vision transformers. I would say it's beyond validation. I feel like to me, these like giant pre-trained vision transformers are kind of state of the art. Like, if I had to do stuff, that's what I would use. However, problems arise when trying to apply this transformer specialized algorithm to convnets. This spurs us to take a deeper look at the fundamental differences between language and image processing, which motivates our solution. Observing the sparse nature of point clouds coincides with masked images, we propose to treat unmasked patches as sparse voxels and use sparse convolution to encode them. We also employ a hierarchical decoder to make full use of the advantage of ConvNet's hierarchy. Our SparK makes mask modeling well suited for any ConvNet and brings a performance leap on downstream tasks. Promising future of BERT-style pre-training on ConvNets has been initially known. Yeah, I mean, they've basically shown that you can do this with ConvNets. ConvNets will live a little bit longer. We hope our exploration and discovery will inspire more work to exploit the potential of ConvNets. All right, that's the paper, guys. It's a paper showing that ConvNets are still here, still alive. In the world of transformers, the ConvNets still survive. Got the GitHub repo here. The main contributors here, Yi Jiang and Ku Tian, are basically the contributors here. And MIT license. So, stuff. Thanks for listening. You guys have a great weekend, and see you guys on Monday.